Hello there, and welcome to the Dreamy Science Channel. I'm so glad you found your way here tonight. Tonight, we're going to explore something truly magnificent: galaxies. Those enormous islands of stars, gas, and mystery that float through the cosmic dark like luminous dreams. We'll drift gently from one fascinating truth to another, learning about spiral arms that turn like slow dancers, about ancient light that has traveled for billions of years just to reach your eyes, and about the gentle rhythms that govern these celestial cities. Let's begin our quiet journey through the most relaxing facts about galaxies. Galaxies drift through space in slow, graceful processions that span millions of years. When we look up at the night sky, everything seems still and eternal, but galaxies are actually in constant, gentle motion, gliding through the universe like vast ships on a cosmic ocean. They don't rush or hurry. They move with the patience of deep time, following invisible currents of gravity and dark matter. Some galaxies travel in small groups, staying close to their companions across the eons. Others journey alone, carrying their billions of stars through the quiet emptiness between galactic neighborhoods. This motion is so slow and stately that entire human civilizations could rise and fall without detecting the slightest change in a galaxy's position. Yet over cosmic time, these migrations reshape the universe itself, bringing distant stellar cities together in gentle collisions that create something new and beautiful. The light from distant galaxies acts like a time machine, showing us the universe as it was long ago. When you look at a galaxy through a telescope, you're not seeing it as it exists today. You're seeing it as it was when that light began its journey toward Earth, sometimes billions of years ago. The most distant galaxies we can observe appear to us as they were when the universe was young, their light carrying stories from cosmic childhood across vast stretches of space and time. This means that every deep photograph of the night sky is actually a historical document, preserving moments from different eras of cosmic history in a single image. The nearest galaxies show us relatively recent times, while the farthest ones whisper of ancient epochs when the first stars were just beginning to shine and the universe was finding its rhythm. Spiral galaxies rotate with a mesmerizing rhythm that has persisted for billions of years. These cosmic pinwheels don't spin like solid objects. Instead, they turn with a fluid grace, their spiral arms maintaining their elegant curves through a delicate dance of gravity and motion. Stars near the center complete their orbits relatively quickly, while those in the outer regions take their time, sometimes requiring hundreds of millions of years to make a single trip around the galactic core. This differential rotation is what keeps the spiral pattern intact, like a slow whirlpool in space that never quite winds itself up. The arms themselves aren't fixed structures, but rather density waves, regions where stars and gas gather temporarily before continuing on their individual paths. It's a cosmic choreography that has been playing out since long before Earth existed, a gentle waltz written in starlight. Some galaxies glow with the soft light of ancient stars that have been burning for most of the universe's existence. These are the elliptical galaxies, smooth and rounded collections of elderly suns that have settled into a quiet, contemplative phase of cosmic life. Unlike their spiral cousins with their active star formation and youthful blue giants, elliptical galaxies shine with the warm, steady glow of red and yellow stars that have been patiently burning their fuel for billions of years. These stellar populations give elliptical galaxies a serene, golden appearance, like cosmic embers that have found their peaceful equilibrium. They rarely form new stars, instead maintaining their gentle radiance through the accumulated light of countless ancient suns. In a way, they represent the universe's capacity for patience and endurance, stellar communities that have found their rhythm and settled into a long, quiet contemplation of eternity. Galaxies are held together by invisible halos of dark matter that extend far beyond their visible edges. What we see when we look at a galaxy, the stars and gas and dust, is only a small part of what's actually there. Surrounding each galaxy is a vast, unseen halo of dark matter, a mysterious substance that doesn't emit or absorb light, but exerts a gentle gravitational influence that keeps everything in place. These halos are enormous, sometimes 10 times larger than the visible galaxy itself, creating invisible boundaries and territories in space. Without this dark matter, galaxies would simply fly apart, their stars scattered like leaves in a cosmic wind. Instead, they remain stable and cohesive, held together by this unseen embrace. It's a reminder that the universe contains far more than what meets the eye, invisible architectures of mass and gravity that provide the foundation for all the light and beauty we can observe. The centers of many galaxies contain supermassive black holes that act like quiet cosmic hearts. These aren't the violent, destructive monsters often portrayed in science fiction, but rather gentle giants that help regulate the life of their galaxy. Most of the time, they sit peacefully at the galactic core, their gravity providing a stable anchor around which billions of stars can orbit safely. They occasionally feed on gas and dust that drifts too close, but they do so with a measured restraint, taking only what the galaxy can spare. In fact, these central black holes seem to play a crucial role in controlling how fast their galaxy forms new stars, sending out gentle feedback that prevents runaway star formation. They're like the steady heartbeat of the galaxy, providing rhythm and stability to the cosmic community around them. Dwarf galaxies are the universe's gentle companions, small stellar neighborhoods that often orbit larger galaxies like cosmic suburbs. These modest collections of stars may contain only a few billion suns, compared to the hundreds of billions found in giants like our Milky Way. But they possess their own quiet charm and importance. Many dwarf galaxies maintain a peaceful relationship with their larger neighbors, orbiting at safe distances for billions of years. They often serve as stellar nurseries, places where new stars can form in the calm environment, away from the more chaotic centers of larger galaxies. Some dwarf galaxies are so faint that they're almost transparent. Their stars spread so thinly that you can see through them to the galaxies beyond. Yet despite their modest nature, they may actually outnumber the giant galaxies, making them the most common type of stellar community in the universe. The space between galaxies contains a thin, warm medium that connects distant stellar islands across the cosmic web. This intergalactic medium is incredibly sparse, containing only a few particles per cubic meter, yet it fills the vast voids between galaxies with a subtle presence, The gas is heated to temperatures of millions of degrees, not by fire but by the gentle influence of gravity and the occasional shock wave from distant cosmic events. This warm medium acts like cosmic weather, flowing along invisible filaments of dark matter that span hundreds of millions of light years. It carries elements forged in ancient stars from one region of the universe to another, slowly redistributing the building blocks of future stars and planets. Though nearly empty by earthly standards, this intergalactic medium represents a quiet form of cosmic circulation, a gentle breathing of matter and energy across the largest scales of space and time. Galaxies can merge together in slow, elegant dances that create entirely new stellar communities. When two galaxies encounter each other, they don't collide like cars in an accident. Instead, they perform a gravitational ballet that unfolds over hundreds of millions of years. As they approach, their gravity begins to distort each other's shape, drawing out long streamers of stars that arc gracefully through space. The galaxies may pass by each other several times, each encounter pulling them closer together until they eventually settle into a stable embrace. During this process, very few individual stars actually collide because they're separated by such vast distances. Instead, the stars simply find new orbits in the combined system, like dancers changing partners in a slow, cosmic waltz. The result is often a larger, more massive galaxy, with a rich history written in the scattered trails of stars that mark the merger's path. Some galaxies shine primarily in infrared light, glowing with the warm radiance of cosmic dust and newborn stars. These infrared galaxies appear dim or even invisible to our eyes, but when viewed with special telescopes that can detect heat radiation, they blaze with hidden fire. The infrared glow comes from dust grains that absorb the intense light of young, hot stars and re-emit it as gentle warmth. This creates a soft, enveloping radiance that permeates the entire galaxy, like a stellar nursery wrapped in cosmic swaddling clothes. Many of these infrared galaxies are in the process of forming stars at a tremendous rate, their gas and dust condensing into new suns faster than in typical galaxies. Yet despite this intense activity, they appear serene and peaceful when viewed in infrared light, glowing with the contentment of a stellar community in the midst of a baby boom. The oldest galaxies we can observe formed when the universe was still in its cosmic childhood, less than 1 billion years after the beginning of time. These ancient stellar cities represent some of the first attempts at galactic architecture, built from the primordial hydrogen and helium that filled the early cosmos. They tend to be smaller and more irregular than modern galaxies, lacking the elegant spiral structure we see in more mature systems. Their stars are different too, formed from gas that contained almost none of the heavy elements that color and enrich the stellar populations of younger galaxies. Observing these ancient galaxies is like looking at cosmic baby pictures, glimpses of how stellar communities learned to organize themselves in the universe's early days. They remind us that even the most fundamental structures in the cosmos had to evolve and develop, learning through trial and experience how to build stable, long-lasting communities of stars. Thank you for joining me on this gentle exploration through the peaceful wonders of galaxies. We've drifted together through cosmic time and space, discovering how these magnificent stellar cities move through the universe with patient grace, how they're held together by invisible embraces of dark matter, and how they dance together in slow gravitational ballets that span millions of years. Each galaxy is a unique community of stars, a cosmic neighborhood with its own character and history, yet all are connected by the subtle threads of gravity and the shared heritage of cosmic evolution. As you rest tonight, remember that somewhere out there, billions of galaxies continue their quiet journeys through space, their stars shining steadily through the darkness, their spiral arms turning with the rhythm of deep time. You are part of this vast cosmic community, made from the same stellar materials that light up these distant islands of stars, connected to the universe's grandest structures by the invisible bonds of physics and the gentle currents of space and time. Galaxy clusters are the universe's largest gravitationally bound communities, vast cosmic cities where hundreds or thousands of galaxies gather in peaceful congregation. These enormous structures span tens of millions of light years and contain more mass than a quadrillion suns, yet they maintain a gentle equilibrium that has persisted for billions of years. The galaxies within a cluster don't sit motionless like houses on a street. Instead, they follow complex orbital paths, weaving between one another in a slow-motion dance choreographed by gravity. Some clusters are dense and compact, their member galaxies huddled close together in cosmic intimacy. Others are more relaxed, their stellar communities spread across vast distances, yet still bound by invisible threads of gravitational attraction. The space between cluster galaxies isn't empty, but filled with hot, thin gas that glows softly in X-ray wavelengths, creating a warm cosmic atmosphere that pervades the entire structure. Lenticular galaxies represent a peaceful middle ground between the spiral and elliptical families, smooth and disc-shaped, but without the dramatic spiral arms of their more flamboyant cousins. These serene stellar systems have exhausted most of their star-forming gas, settling into a quiet phase of galactic life where they shine with the steady light of mature stellar populations. They often display a subtle central bulge surrounded by a smooth, featureless disk that glows with the warm colors of older stars. Lenticular galaxies are common in galaxy clusters, where the gentle harassment from neighboring galaxies has gradually stripped away their star-forming material, leaving behind these contemplative stellar communities. They represent a kind of cosmic retirement. Stellar neighborhoods have found their equilibrium and now spend their time in quiet contemplation, their billions of stars following predictable orbits in perfect gravitational harmony. The cosmic microwave background radiation provides a gentle, uniform glow that bathes every galaxy in the faint afterglow of the universe's birth. This ancient light, stretched and cooled by billions of years of cosmic expansion, fills all of space with a temperature just a few degrees above absolute zero. It's the universe's memory of its hot, dense beginning, now diluted to a whisper but still present everywhere. Every galaxy, from the smallest dwarf to the largest giant, moves through this sea of primordial radiation like a ship sailing through luminous fog. The microwave background is remarkably smooth and uniform, varying by only tiny fractions from place to place. Yet these minuscule variations provided the seeds from which all galaxies eventually grew. It's a cosmic lullaby that has been playing since the universe was young, a gentle radiation that connects every stellar community to the shared origin of all things. Galactic winds blow gently from star-forming regions, carrying enriched material into the spaces between galaxies in a process that resembles cosmic breathing. When massive stars are born, live their brief lives, and die in spectacular explosions, they heat and accelerate the surrounding gas, creating outflows that can extend far beyond the galaxy's visible boundaries. These winds aren't violent storms, but rather gentle breezes on a galactic scale, moving at speeds that seem fast by human standards, but represent a leisurely pace in cosmic terms. The winds carry heavy elements forged in stellar cores, distributing the chemical products of star formation throughout the galaxy and beyond. Over time, this process enriches the intergalactic medium with the building blocks needed for future generations of stars and planets. It's a form of cosmic recycling, where galaxies slowly exhale the products of stellar evolution, contributing to the chemical complexity of the universe. Polar ring galaxies are rare and beautiful cosmic anomalies, where a ring of stars and gas orbits perpendicular to the main galactic disk, creating structures that look like celestial gyroscopes. These unusual configurations likely form when one galaxy captures material from a smaller companion, but instead of the material settling into the existing disk, it maintains its original orbital plane. The result is a galaxy with two distinct components: the original disk continuing its rotation in one plane, while the captured ring circles at right angles. These systems are extraordinarily stable, with both components maintaining their separate orbital families for billions of years. Polar ring galaxies represent the universe's capacity for creating unexpected beauty from chance encounters, cosmic accidents that result in some of the most aesthetically striking structures in the night sky. The local void is an enormous region of space where our own cosmic neighborhood resides, a relatively empty bubble in the cosmic web that spans hundreds of millions of light-years. This vast region contains far fewer galaxies than average, creating a kind of cosmic suburb where stellar communities have more room to spread out and evolve in peaceful isolation. Living within a void doesn't mean we're truly alone, but rather that the nearest major concentrations of galaxies are farther away than they would be in a typical region of the universe. The void provides our local group of galaxies with a quieter environment, free from the gravitational influences that might disrupt galactic evolution in denser regions. It's like living in a cosmic countryside, where the pace of change is gentler and the interactions between neighboring galaxies are more measured and predictable. Ultra-diffuse galaxies are ghostly stellar communities that stretch across enormous distances while containing relatively few stars, creating some of the most ethereal structures in the cosmos. These galaxies can be as large as our Milky Way, but contain 100 times fewer stars, making them so faint and transparent that they're incredibly difficult to detect. Their stars are spread so thinly that if you could somehow visit one of these galaxies, the night sky would appear almost as dark and empty as intergalactic space. Yet despite their tenuous nature, Ultra-diffuse galaxies are surprisingly stable, held together by massive halos of dark matter that provide the gravitational scaffolding needed to maintain their structure. They represent the universe's ability to create order and stability even in the most delicate and seemingly fragile configurations. The Great Wall of Galaxies is a vast structure that stretches across hundreds of millions of light years, representing one of the largest coherent features in the observable universe. This isn't a physical barrier, but rather a concentration of galaxies arranged in a thin sheet that extends across enormous distances. The Great Wall demonstrates how matter organizes itself on the largest scales, following the invisible framework provided by dark matter filaments. Galaxies within the wall aren't necessarily interacting directly with each other, but they share a common gravitational environment that has guided their formation and evolution. The structure is so large that light takes hundreds of millions of years to cross from one end to the other. Yet it represents a coherent feature in the cosmic web, a demonstration of how the universe organizes itself into patterns of breathtaking scale and beauty. Red dwarf galaxies burn their stellar fuel so slowly that they could continue shining for trillions of years, far longer than the current age of the universe. These modest stellar communities are dominated by small, cool stars that consume their nuclear fuel at a measured pace, creating the potential for extraordinarily long-lived galactic civilizations. Unlike more massive stars that burn brightly and die young, the red dwarfs that populate these galaxies could continue their steady nuclear burning long after larger, more dramatic stars have exhausted their fuel and faded away. This creates the possibility of galactic communities that remain stable and active for cosmological ages, providing consistent environments where complex processes could unfold over previously unimaginable timescales. Red dwarf galaxies represent the universe's capacity for patience and endurance, stellar communities that prioritize longevity over immediate brightness. Fossil groups are the quiet remains of what were once rich galaxy clusters, now reduced to a single large elliptical galaxy surrounded by the faint traces of its former companions. These systems form when a galaxy group or small cluster evolves in isolation, allowing the largest member to gradually cannibalize its neighbors through a series of gentle mergers. The process unfolds over billions of years, with each merger adding mass to the central galaxy while erasing the individual identities of the smaller members. What remains is a massive elliptical galaxy sitting at the center of an extended halo of hot gas, the only evidence of the rich community that once existed there. Fossil groups represent the ultimate fate of many galaxy groups, a peaceful consolidation where separate stellar communities gradually merge into a single unified system. Active galactic nuclei in some systems produce jets of material that extend far beyond the host galaxy, creating enormous structures that can span millions of light years, yet maintain remarkably straight paths through space. These jets aren't chaotic explosions, but highly organized flows of particles moving at nearly the speed of light, guided by magnetic fields and remaining coherent across distances that dwarf the galaxies that produce them. The jets often terminate in radio lobes, regions where the high-speed material encounters the thin gas of intergalactic space and creates vast bubbles of energized particles. Despite their enormous scale and high velocities, these structures can persist for millions of years, demonstrating the universe's ability to create and maintain order even in its most energetic phenomena. The jets carve cavities in the surrounding medium, creating cosmic architecture on the largest scales. Dwarf spheroidal galaxies are among the most common types of stellar systems in the universe, yet they're so faint that they remain invisible to casual observation. These modest communities contain only millions of stars compared to the hundreds of billions found in larger galaxies, and their stars are spread across volumes of space that make them incredibly diffuse and difficult to detect. Many dwarf spheroidals orbit larger galaxies as loyal satellites, following elliptical paths that bring them close to their massive companions without ever merging completely. They're dominated by old red stars and contain very little gas, suggesting that they formed their stellar populations long ago and have since settled into a quiet phase of galactic evolution. These systems represent the universe's tendency toward modesty and understatement, stellar communities that prioritize stability and longevity over dramatic displays of cosmic fireworks. The zone of avoidance is a region of sky where our view of distant galaxies is blocked by the dust and stars of our own Milky Way, creating a cosmic blind spot that hides entire populations of stellar systems from direct observation. This zone spans roughly 20% of the sky, encompassing the regions where our galaxy's disk appears thickest and most opaque. Astronomers must use special techniques, including radio and infrared observations that can penetrate the dust, to study the galaxies hidden behind this cosmic curtain. The zone of avoidance reminds us that our perspective on the universe is inherently limited by our location within our own galaxy, and that vast regions of the cosmic landscape remain partially hidden from view. It's a humbling reminder of the universe's enormity and the challenges we face in trying to understand its full scope and structure from our particular vantage point in space and time. Galactic cannibalism occurs through gentle gravitational encounters rather than violent collisions, as larger galaxies slowly absorb their smaller companions over cosmic time. When a massive galaxy encounters a dwarf system, the process unfolds with remarkable patience, taking hundreds of millions of years to complete. The smaller galaxy doesn't disappear suddenly, but gradually loses its stars to the gravitational pull of its larger neighbor. These stars don't crash into anything, but simply find new orbital paths within the expanded stellar community. The process leaves behind faint stellar streams, ghostly trails of stars that mark the path of the consumed galaxy, like cosmic breadcrumbs scattered across the night sky. These streams can persist for billions of years, serving as archaeological evidence of ancient galactic encounters. The cannibalistic process is so gentle that individual stars experience no trauma during the transition, continuing their nuclear burning as they adapt to their new gravitational environment. Starburst galaxies experience periods of intense stellar birth that illuminate entire galactic regions with the brilliant blue light of young, massive stars. These cosmic baby booms occur when something triggers the rapid collapse of gas clouds throughout the galaxy. Perhaps a close encounter with another stellar system, or the compression of material in a galactic collision. During these episodes, stars form at rates hundreds of times faster than normal, creating stellar nurseries that glow with intense ultraviolet radiation. The newborn stars are often clustered together in brilliant associations that can outshine the rest of the galaxy combined. Yet despite their intensity, starburst episodes are relatively brief on cosmic timescales, typically lasting only a few tens of millions of years before the available gas is exhausted or dispersed. These periods represent the universe's capacity for sudden bursts of creativity, moments when galactic communities experience rapid growth and renewal. Ring galaxies form through cosmic collisions that create expanding waves of star formation, resulting in spectacular structures that resemble cosmic ripples frozen in starlight. These unusual systems typically form when a smaller galaxy passes through the disk of a larger spiral, creating a disturbance that propagates outward like ripples on a pond. As this wave of compression moves through the galactic disk, it triggers intense star formation, creating a ring of brilliant blue stars that expands over millions of years. The original spiral structure is often disrupted by the encounter, leaving behind a central region surrounded by one or more rings of active stellar birth. Ring galaxies are relatively rare and temporary structures, as the rings gradually fade as star formation subsides and the galaxy settles into a new equilibrium. They represent cosmic accidents that create unexpected beauty, demonstrations of how chance encounters can sculpt matter into forms of surprise and elegance. Seyfert galaxies contain active central regions that produce gentle, steady emissions across the electromagnetic spectrum, creating stellar systems with quietly energetic hearts. Unlike their more dramatic cousins, the quasars, Seyfert galaxies maintain a subtle balance between activity and tranquility. Their central black holes consume material at a measured pace, producing radiation that's detectable but not overwhelming. This creates galaxies that appear relatively normal in visible light, but reveal their active nature when observed in other wavelengths. The emission comes from gas that's being heated as it spirals toward the central black hole, creating a warm, glowing accretion disk that radiates steadily across millions of years. Seyfert galaxies demonstrate that cosmic activity doesn't always manifest as dramatic violence, but can instead take the form of sustained, gentle processes that enrich their galactic environments with energy and elements. Peculiar galaxies display unusual morphologies that don't fit into the standard classification schemes, representing cosmic experiments in galactic architecture. These systems might show distorted shapes, unusual color patterns, or asymmetric features that hint at complex evolutionary histories. Some peculiar galaxies display long tidal tails that stretch across hundreds of thousands of light years, evidence of gravitational encounters that pulled streams of stars into space. Others show ring-like structures, offset nuclei, or irregular distributions of star formation that create unique cosmic signatures. Each peculiar galaxy tells a story of interaction, evolution, or environmental influence that has shaped it into something distinctive. They remind us that the universe's creativity extends beyond the familiar spiral and elliptical forms, encompassing a rich variety of structures that emerge from the complex interplay of gravity, gas dynamics, and stellar evolution. The local sheet is a flattened distribution of nearby galaxies that includes our own Milky Way, creating a cosmic neighborhood where stellar systems are arranged in a relatively thin layer. This structure spans about 7 million light-years and contains several dozen galaxies, including the Andromeda Galaxy and various dwarf systems. The galaxies within the local sheet share similar motions through space, suggesting they're part of a coherent structure that formed early in cosmic history. The sheet itself moves through the universe as a unit, carried along by the larger scale flows that govern galactic motion on cosmic scales. Living within this structure provides our region with a degree of gravitational stability, as the member galaxies help to shield each other from the disruptive influences of more distant, massive structures. Compact groups of galaxies represent dense concentrations of stellar systems that exist in gravitational harmony, despite their close proximity to one another. These tight-knit communities typically contain 4 to 8 major galaxies packed into regions smaller than our local group. Yet they can remain stable for billions of years. The member galaxies follow complex orbital paths that bring them close together without causing immediate mergers, creating dynamic systems where gravitational influences are strong but carefully balanced. Some compact groups show evidence of ongoing interactions, with tidal streams and distorted morphologies indicating that the member galaxies are slowly evolving through their mutual gravitational influences. Others appear remarkably stable, their members maintaining distinct identities while participating in the group's collective gravitational dance. Void galaxies are isolated stellar systems that exist in the vast empty regions between major galactic concentrations, creating cosmic hermits that evolved in unusual solitude. These galaxies often display different characteristics than their counterparts in denser environments, as they've been largely free from the gravitational influences that shape galactic evolution in clusters and groups. Many void galaxies are actively forming stars, having retained their gas supplies in the quiet environment where tidal stripping and ram pressure effects are minimal. They tend to be bluer and less massive than galaxies in denser regions, suggesting that isolation preserves certain aspects of galactic youth. Void galaxies demonstrate how environment shapes cosmic evolution, showing what happens when stellar systems develop in the universe's quietest neighborhoods. Blue compact dwarf galaxies are small stellar systems undergoing intense periods of star formation that illuminate them with the brilliant light of young, massive stars. These galaxies appear as small blue knots in deep sky surveys, their modest size belied by their energetic stellar birth rates. Despite containing relatively few stars overall, they can outshine much larger galaxies during their starburst episodes. The star formation often occurs in just a few compact regions within the galaxy, creating bright stellar associations that dominate the system's appearance. Many blue compact dwarfs contain large reservoirs of pristine gas, suggesting they're relatively unevolved systems that have retained much of their original star-forming material. They represent the universe's continued capacity for stellar creation, showing that even modest galactic systems can experience dramatic episodes of cosmic renewal. luminous infrared galaxies glow primarily in heat radiation, their visible light absorbed by cosmic dust and re-emitted as gentle warmth that pervades the entire stellar system. These systems often result from galaxy mergers that have compressed gas and dust into dense configurations, triggering intense star formation that's hidden from optical view but blazes brilliantly in infrared wavelengths. The dust that obscures these galaxies also protects the star-forming regions from the disruptive effects of stellar radiation, creating cocoons where new stars can form in relative safety. Many luminous infrared galaxies are in transitional phases, evolving from gas-rich spirals into more quiescent elliptical systems through the transformative process of merger-induced star formation. They represent hidden stellar factories, cosmic foundries where new generations of stars are born in warm, dusty environments. Galaxy harassment describes the gentle but persistent gravitational influences that cluster galaxies exert on one another, gradually transforming their shapes and star formation rates through repeated close encounters. Unlike dramatic mergers, harassment works through cumulative effects, with multiple high-speed encounters over billions of years slowly stripping gas from spiral galaxies and distorting their morphologies. The process is particularly effective in rich galaxy clusters, where the high velocities of member galaxies create frequent but brief gravitational interactions. Over time, harassment can transform a gas-rich spiral into a gas-poor lenticular or elliptical galaxy, changing both its appearance and its capacity for forming new stars. This cosmic erosion demonstrates how even, gentle influences can produce dramatic changes when sustained over sufficiently long periods. Brightest cluster galaxies are the luminous monarchs of galaxy clusters, massive elliptical systems that sit at the gravitational centers of their cosmic communities. These giants often contain trillions of stars and can be 10 times more massive than typical large galaxies, having grown through billions of years of mergers and accretion. They typically show little ongoing star formation, instead shining with the steady light of ancient stellar populations that formed early in cosmic history. Many brightest cluster galaxies are surrounded by extensive envelopes of faint starlight, evidence of the numerous smaller galaxies they've consumed over cosmic time. Their central locations and enormous masses make them natural gathering points for the hot gas that fills galaxy clusters, creating systems where galactic evolution and cluster physics intersect in complex ways. Radio galaxies extend far beyond their visible boundaries, through enormous lobes of energized particles that can span millions of light years yet remain invisible to optical telescopes. These vast structures form when jets of material from the galaxy's central black hole travel at nearly the speed of light into the surrounding intergalactic medium, where they inflate enormous bubbles of radio-emitting plasma. The lobes often dwarf the host galaxy itself, creating cosmic architecture on scales that challenge our understanding of how energy can be transported and organized across such immense distances. Despite their enormous size, these radio structures can persist for tens of millions of years, maintaining their coherent shape even as they drift through the thin gas between galaxies. They represent some of the largest single objects in the universe, yet they remain completely invisible to our eyes, detectable only through radio telescopes that can sense their gentle magnetic whispers. Fossil galaxies are ancient stellar systems that formed early in cosmic history and have remained largely unchanged ever since, preserving conditions from the universe's youth like cosmic time capsules. These rare objects manage to avoid the mergers and interactions that have transformed most other galaxies over billions of years, allowing them to maintain their original characteristics in remarkable detail. They often contain unusually old stellar populations with chemical compositions that reflect the simpler elements available in the early universe, before generations of stellar evolution had enriched the cosmic medium with heavy elements. Studying fossil galaxies provides astronomers with direct glimpses into galactic conditions that existed when the universe was young, offering insights into how the first stellar communities organized themselves in the primordial cosmos. They stand as monuments to cosmic preservation, stellar systems that chose stability over change and have maintained their ancient character across the eons. Tidal dwarf galaxies are newly formed stellar systems born from the gravitational debris of galactic encounters, representing cosmic recycling on the grandest scales. When two large galaxies interact, their mutual gravity can pull long streams of stars and gas into space, and sometimes these tidal tails can condense into self-gravitating objects that become independent galaxies in their own right. These newborn systems inherit the chemical composition of their parent galaxies, making them unusually metal-rich for such small objects. Tidal dwarfs often display active star formation, as the compression that created them also triggers the collapse of gas clouds into new stellar nurseries. They demonstrate the universe's ability to create new galactic communities from the disrupted remains of older ones, showing how cosmic destruction can simultaneously become cosmic creation. These systems are relatively short-lived on cosmic timescales, eventually falling back into their parent galaxies or dispersing their stars into the intergalactic medium. Galaxy groups represent intimate stellar neighborhoods where individual galaxies can maintain their identities while participating in shared gravitational relationships that span millions of years. These loose associations typically contain between 3 and 50 galaxies bound together by their mutual attraction, creating communities that are more cohesive than random distributions, but less dense than major galaxy clusters. The members of galaxy groups often show evidence of gentle interactions with distorted shapes or enhanced star formation rates that result from their gravitational relationships. Many groups contain a mix of spiral and elliptical galaxies, creating diverse communities where different types of stellar systems coexist in gravitational harmony. The local group, which includes our own Milky Way and the Andromeda Galaxy, serves as a familiar example of these cosmic neighborhoods where galaxies share space and influence each other's evolution over cosmic time. Intermediate mass black holes may reside in the centers of some dwarf galaxies, creating scaled-down versions of the supermassive objects found in larger stellar systems. These modest gravitational anchors would be thousands rather than millions of times more massive than our Sun, providing just enough central mass to influence their galaxy's structure and evolution. The relationship between a galaxy's mass and its central black hole appears to extend down to the smallest stellar systems, suggesting that this cosmic partnership represents a fundamental aspect of galactic architecture. Dwarf galaxies with central black holes often show subtle signs of nuclear activity, with gentle emissions that hint at the presence of these hidden gravitational engines. The discovery of intermediate mass black holes would fill an important gap in our understanding of how these extreme objects form and evolve, providing insights into the processes that create cosmic structure on all scales. Galactic archaeology uses the chemical signatures preserved in stellar atmospheres to reconstruct the formation histories of galaxies, reading cosmic stories written in starlight. Each generation of stars inherits and modifies the chemical composition of its galactic environment, creating a detailed record of stellar evolution that astronomers can decode through spectroscopic analysis. Ancient stars preserve the chemical conditions that existed when they formed, serving as fossil records of their galaxy's early history. By studying the abundances of different elements in stars of various ages, astronomers can trace how galaxies assembled their mass when they experienced periods of intense star formation, and how they exchanged material with their cosmic neighbors. This stellar archaeology reveals that most galaxies have complex histories involving mergers, interactions, and episodes of star formation that have shaped their current appearance and composition. Super-thin galaxies are extremely flattened stellar systems that appear as cosmic needles when viewed edge-on, representing extreme examples of galactic rotation and structural organization. These rare objects have disk-to-thickness ratios that far exceed those of typical spiral galaxies, creating structures that seem impossibly delicate, yet remain stable over cosmic time. Their extreme flatness results from rapid rotation combined with relatively low stellar velocity dispersions, conditions that allow gravity to compress the stellar disk into remarkably thin configurations. Many super-thin galaxies display active star formation despite their unusual morphology, with chains of bright stellar nurseries arranged along their narrow disks. They challenge our understanding of galactic stability, demonstrating that stellar systems can achieve structural configurations that seem to push the boundaries of what gravity and rotation can maintain in equilibrium. Low surface brightness galaxies are ethereal stellar systems so diffuse that they barely stand out against the darkness of space, representing cosmic communities that prioritize subtlety over brilliance. These ghostly objects can be as massive as normal galaxies, but spread their stars across such large volumes that they appear faint and nearly transparent. Their low stellar densities create environments where star formation proceeds at a leisurely pace, resulting in galactic communities dominated by old stellar populations that burn with gentle, steady light. Many low-surface brightness galaxies contain large amounts of dark matter, making them excellent laboratories for studying the properties of this mysterious substance. They remind us that the universe contains vast numbers of modest stellar systems that prefer to exist in quiet obscurity rather than blazing with obvious cosmic fire. Compact elliptical galaxies are dense, massive stellar systems that pack enormous numbers of stars into relatively small volumes, creating some of the most concentrated galactic environments in the universe. These objects often result from tidal stripping processes that remove the outer regions of larger galaxies, leaving behind their dense cores as independent systems. Despite their small sizes, compact ellipticals can contain stellar populations as massive as much larger galaxies, creating environments where stars are packed together at densities far exceeding those found in typical galactic neighborhoods. Many of these systems are found near the centers of galaxy clusters, where gravitational interactions are strong enough to sculpt galaxies into these unusual configurations. They represent cosmic compression at its most extreme, stellar communities that have been squeezed by gravity into forms of remarkable density and concentration. Shell galaxies display concentric arcs of starlight that surround their central regions like cosmic ripples, evidence of ancient mergers that continue to influence galactic structure billions of years after the original encounter. These delicate shells form when a smaller galaxy falls into a larger elliptical system, creating waves of stellar density that propagate outward through the gravitational field. The shells can persist for enormous periods of time, serving as archaeological evidence of merger events that occurred when the universe was much younger. Each shell represents a different phase of the merger process, with multiple concentric structures recording the complex gravitational dynamics that occurred during the galactic collision. Shell galaxies demonstrate the universe's capacity for preserving evidence of ancient events in forms of subtle beauty, cosmic memories written in the gentle arrangement of starlight. Jellyfish galaxies are spiral systems undergoing ram pressure stripping as they move through the hot gas of galaxy clusters, creating spectacular tails of star-forming material that trail behind them like cosmic streamers. As these galaxies orbit through their cluster environment, the pressure of the surrounding hot gas strips away their own interstellar medium, pulling long filaments of gas and young stars into space. The stripped material often continues to form stars even after being removed from the galaxy, creating chains of stellar nurseries that extend far beyond the original galactic disk. This process gradually transforms gas-rich spirals into gas-poor systems, demonstrating how environmental effects can dramatically alter galactic evolution. Jellyfish galaxies represent cosmic metamorphosis in action, stellar systems caught in the process of adapting to new gravitational and hydrodynamical environments. Green Valley galaxies occupy a transitional zone between star-forming and quiescent stellar systems, representing cosmic communities in the process of evolutionary change. These galaxies display intermediate colors that result from declining star formation rates, as their stellar populations gradually shift from the blue light of young stars to the redder hues of older stellar generations. The Green Valley represents a relatively brief phase in galactic evolution, a period when stellar systems are transforming from active star-forming spirals into more quiescent elliptical configurations. Many Green Valley galaxies show evidence of recent interactions or environmental influences that have begun to shut down their star formation, creating systems in transition between different phases of cosmic life. They remind us that galactic evolution is not a static process, but rather a continuous journey through different states of stellar community organization and activity. Coma cluster galaxies exist in one of the richest galactic environments in the nearby universe, where thousands of stellar systems congregate in a cosmic metropolis that spans tens of millions of light years. This enormous cluster contains galaxies of every type and size, from giant ellipticals that dominate the central regions to small dwarf systems that orbit in the cluster's outer suburbs. The gravitational environment is so complex that member galaxies experience constant influences from their neighbors, leading to ongoing evolution through tidal interactions and environmental effects. The cluster's center is filled with hot gas that glows in X-ray wavelengths, creating a luminous atmosphere that pervades the entire system. Coma represents galactic civilization at its most developed, a cosmic city where stellar communities have learned to coexist in one of the universe's most crowded neighborhoods. Ultra-compact dwarf galaxies are among the densest stellar systems in the universe, packing millions of stars into regions smaller than typical globular clusters, yet maintaining their status as independent galactic entities. These unusual objects may represent the stripped cores of larger dwarf galaxies that lost their outer regions during gravitational encounters, leaving behind their dense central concentrations as fossil remnants. Despite their small sizes, ultra-compact dwarfs often contain supermassive black holes, creating systems where the central gravitational anchor represents a significant fraction of the total mass. They blur the distinction between large star clusters and small galaxies, occupying a unique niche in the cosmic hierarchy of stellar systems. These objects demonstrate that galactic architecture can be compressed into remarkably compact configurations while still maintaining the complex internal structure that defines true galactic systems. Brightest group galaxies serve as the central anchors of smaller galactic communities, playing roles similar to their cluster counterparts, but in more intimate cosmic neighborhoods. These systems often show evidence of having grown through the gradual accretion of smaller group members, displaying extended stellar envelopes and multiple nuclei that record their merger histories. Their central locations make them natural targets for ongoing interactions with other group members, creating dynamic systems where galactic evolution continues through gravitational encounters and material exchange. Many brightest group galaxies maintain active star formation despite their large masses and central positions, suggesting that group environments can be more conducive to ongoing galactic growth than harsher conditions found in major clusters. They represent cosmic leadership on smaller scales, stellar systems that serve as gravitational and dynamical centers for their local galactic communities. Satellite galaxies orbit their massive companions like cosmic moons, following predictable paths through space that have persisted for billions of years. These smaller stellar systems maintain their independence while remaining gravitationally bound to larger galaxies, creating hierarchical relationships that span enormous distances. The Magellanic Clouds that accompany our own Milky Way represent familiar examples of this cosmic companionship. Two modest galaxies that have traced their orbits around our stellar neighborhood for countless eons. Many satellite systems show evidence of tidal interactions with their hosts, displaying distorted shapes or streams of stars that mark their gravitational encounters. Yet despite these influences, most satellites retain their distinct identities, continuing to form new stars and evolve as independent stellar communities, even while participating in larger galactic relationships. Intermediate redshift galaxies exist at cosmic distances that allow us to observe them as they appeared several billion years ago, during an epoch when the universe was more actively forming stars and assembling galactic structures. These systems often display more irregular morphologies than their local counterparts, reflecting the more chaotic conditions that prevailed when cosmic evolution was proceeding at a faster pace. Many intermediate redshift galaxies show intense star formation activity, with bright stellar nurseries that produce new suns at rates far exceeding those found in nearby stellar systems. Their observations provide crucial insights into how galaxies have evolved over cosmic time, revealing the processes that transformed the universe from its early, more active phase to the quieter cosmic neighborhood we observe today. Intra-cluster light fills the spaces between cluster galaxies with a faint, diffuse glow composed of stars that have been stripped from their original homes during gravitational encounters. This ethereal illumination represents the accumulated stellar debris from billions of years of galactic interactions, creating a kind of cosmic atmosphere that pervades entire cluster environments. The intracluster stars follow the gravitational potential of the cluster as a whole rather than belonging to individual galaxies, creating stellar populations that exist in the spaces between galactic communities. Despite their homeless status, these stars continue to burn steadily, contributing to the overall luminosity of galaxy clusters in ways that are only detectable through careful astronomical analysis. Galaxy protoclusters represent the early stages of cluster formation, cosmic construction sites where future galactic metropolises are still assembling from smaller components. These structures exist at such great distances that we observe them as they appeared when the universe was young, providing glimpses into how the largest gravitational structures organize themselves over cosmic time. Protoclusters often contain numerous actively star-forming galaxies packed into relatively small volumes, creating environments rich in cosmic activity and interaction. The member galaxies are still in the process of settling into their final configurations, displaying the kinds of dynamic behavior that characterized galactic evolution during the universe's more energetic youth. Post-starburst galaxies have recently ceased their star formation activity, displaying the spectroscopic signatures of stellar populations that formed in intense bursts before the galactic environment became quiescent. These systems often result from galaxy mergers or other disruptive events that first triggered rapid star formation and then removed or heated the remaining gas supplies. The absence of ongoing stellar birth creates galaxies dominated by intermediate-age stars, giving them distinctive colors and spectra that allow astronomers to identify them as systems in transition. Post-starburst galaxies represent cosmic communities that have experienced dramatic changes in their stellar formation histories, providing insights into the processes that can rapidly transform galactic environments. Dwarf elliptical galaxies are small, smooth stellar systems that lack the spiral structure of their larger cousins, but maintain stable configurations through the patient influence of their dark matter halos. These modest communities often orbit larger galaxies as satellite systems, following elliptical paths that bring them close to their massive companions without causing immediate mergers. Their stellar populations tend to be old and metal-poor, suggesting that they formed their stars early in cosmic history and have since evolved in relative isolation. Many dwarf ellipticals show evidence of past interactions that stripped away their gas supplies, leaving behind stellar communities that shine with the gentle light of ancient suns. Galaxy filaments represent the largest coherent structures in the universe, vast networks of dark matter and galaxies that stretch across hundreds of millions of light-years like cosmic highways, connecting distant stellar communities. These filaments form the backbone of the cosmic web, channeling matter and energy between different regions of the universe through gravitational processes that operate on the grandest possible scales. Galaxies within filaments often show aligned orientations and enhanced star formation rates, evidence of the large-scale forces that influence galactic evolution along these cosmic thoroughfares. The filamentary network creates a kind of cosmic infrastructure that guides the flow of matter and the formation of structure throughout the observable universe. Central dominant galaxies occupy the gravitational centers of rich galaxy clusters, serving as cosmic capitals for some of the largest bound structures in the universe. These massive elliptical systems often display multiple nuclei and complex internal structure, evidence of the numerous mergers that built them through billions of years of galactic accretion. Their central locations expose them to constant gravitational influences from cluster members, creating dynamic environments where ongoing evolution continues through tidal interactions and occasional mergers. Many central dominant galaxies are surrounded by extensive coronas of hot gas that extends far beyond their visible boundaries, creating hybrid systems where galactic and cluster physics intersect in complex ways. Galaxy formation simulations reveal how cosmic structures emerge from the subtle density variations present in the early universe, growing through gravitational collapse and merger processes that span billions of years. These computational models demonstrate how dark matter halos provide the scaffolding for galactic assembly, attracting ordinary matter that eventually condenses into stars and planetary systems. The simulations show that galaxy formation is not a smooth, uniform process, but rather proceeds through episodic events involving mergers, gas accretion, and environmental influences that shape each stellar system's unique evolutionary history. Modern simulations can reproduce many of the observed properties of real galaxies, providing theoretical frameworks for understanding how cosmic structure develops over time. Galactic bars are elongated stellar structures that form in the central regions of many spiral galaxies, creating cosmic stirring mechanisms that redistribute matter and influence star formation patterns throughout their host systems. These bars rotate as solid bodies, maintaining their structural integrity over hundreds of millions of years, while channeling gas toward galactic centers where it can fuel star formation or feed central black holes. The formation of galactic bars represents a kind of cosmic self-organization, where gravitational instabilities in rotating stellar disks naturally evolve toward these elongated configurations. Barred galaxies often display enhanced star formation rates and more active central regions, demonstrating how internal galactic dynamics can influence cosmic evolution. Bulgeless galaxies are pure disk systems that lack the central stellar concentrations found in most spiral galaxies, creating unusually flat stellar distributions that extend all the way to their rotational centers. These rare systems challenge standard models of galaxy formation, which typically predict that stellar disks should develop central bulges through merger processes and gravitational instabilities. Bulgeless galaxies often display ongoing star formation and relatively undisturbed morphologies, suggesting that they have avoided the major interactions that typically disrupt galactic structure and build central stellar concentrations. Their existence demonstrates that galactic evolution can follow multiple pathways, with some stellar systems maintaining their original disk configuration throughout cosmic history. Galaxy mass functions describe the relative numbers of stellar systems with different masses, revealing that the universe contains many more small galaxies than large ones, in a relationship that follows predictable mathematical patterns. This cosmic census shows that dwarf galaxies vastly outnumber their more massive counterparts, creating galactic populations dominated by modest stellar communities that often remain difficult to detect and study. The mass function provides important constraints on models of galaxy formation, as successful theories must explain both the abundance of small systems and the relative rarity of galactic giants. Understanding these statistical relationships helps astronomers predict the properties of galactic populations in different cosmic environments and revolutionary epochs. Fossil galaxy groups represent the end states of galactic evolution in small group environments, where all but the most massive member have been consumed through a series of mergers that unfold over cosmic time. These systems contain single large elliptical galaxies surrounded by extended halos of hot gas, the only remaining evidence of the rich stellar communities that once populated these regions. The merger process that creates fossil groups operates through gravitational dynamical friction, which causes smaller galaxies to spiral inward and eventually merge with the central system. Fossil groups demonstrate how galactic cannibalism can completely reorganize stellar communities, creating final states where individual galactic identities have been erased through gravitational consolidation. Brightest infrared galaxies represent some of the most luminous stellar systems in the universe, shining primarily in heat radiation produced by cosmic dust, heated by intense star formation or active galactic nuclei. These extraordinary objects often result from major galaxy mergers that compress vast amounts of gas and dust into compact configurations where stellar birth proceeds at tremendous rates. The infrared luminosity of these systems can exceed that of hundreds of normal galaxies combined, yet they often appear relatively modest in visible light due to the obscuring effects of their dust content. They represent cosmic extremes where galactic evolution proceeds at accelerated rates, creating stellar systems that briefly achieve luminosities comparable to entire galaxy clusters. Compact galaxy groups create some of the most dynamically active environments in the universe, where multiple stellar systems interact within volumes comparable to individual large galaxies. These dense configurations generate complex gravitational fields that constantly influence member galaxies through tidal forces, triggering enhanced star formation rates and gradual morphological evolution. The proximity of group members creates opportunities for direct galactic encounters that can strip away gas supplies, distort stellar distributions, and occasionally trigger complete mergers between participating systems. Despite their small scales, compact groups demonstrate many of the same evolutionary processes found in much larger galaxy clusters, serving as cosmic laboratories where galactic interaction physics can be studied in detail. Ultra-luminous infrared galaxies achieve their extraordinary brightness through merger-induced starbursts that convert enormous gas reservoirs into new stellar populations within relatively brief cosmic periods. These systems often display disturbed morphologies and complex internal structure, evidence of the ongoing gravitational interactions that fuel their intense stellar formation activity. The merger process not only triggers rapid star formation, but also channels gas towards central regions, where it can feed supermassive black holes, creating hybrid systems where stellar and nuclear activity both contribute to the overall luminosity. Ultraluminous infrared galaxies may represent transitional phases in galactic evolution, transforming gas-rich spiral systems into more quiescent ellipticals, configurations through dramatic episodes of star formation and black hole growth. Void wall galaxies exist along the boundaries of cosmic voids, creating chains and sheets of stellar systems that define the edges of the universe's largest empty regions. These boundary environments often show enhanced galaxy formation activity, as matter flows along void walls create conditions favorable for stellar system assembly and evolution. Void wall galaxies frequently display active star formation and relatively undisturbed morphologies, suggesting that their locations provide optimal conditions for ongoing galactic growth. The wall environments also facilitate galaxy interactions and group formation, creating cosmic neighborhoods where stellar systems can influence each other's evolution while remaining relatively isolated from the denser cluster environments found elsewhere in the universe. Stripped spiral galaxies have lost most or all of their interstellar gas through environmental processes, transforming them from actively star-forming systems into quiescent stellar communities dominated by aging stellar populations. This stripping typically occurs in dense cluster environments, where ram pressure from hot intracluster gas removes the galactic gas supplies that fuel ongoing star formation. The process can be remarkably efficient, completely transforming galactic properties within a few 100 million years of cluster membership. Stripped spirals often retain their disk morphologies even after losing their gas, creating systems that appear spiral-like in structure but lack the young blue stars typically associated with spiral arms. Galaxy harassment effects accumulate over cosmic time, as repeated high-speed encounters gradually transform the properties of cluster member galaxies through cumulative gravitational influences. Unlike dramatic mergers, harassment works through multiple brief interactions that individually produce modest effects, but collectively can completely alter galactic characteristics over billions of years. The process is particularly effective in rich cluster environments where galaxy velocities are high and encounter rates are frequent, creating conditions where even minor interactions can accumulate into major evolutionary influences. Harassment can strip away outer stellar regions, heat stellar velocity dispersions, and disrupt spiral structure, gradually converting gas-rich disk galaxies into or spheroidal configurations. Red sequence galaxies represent a cosmic retirement community, stellar systems that have ceased active star formation and settled into a phase characterized by the steady burning of ancient stellar populations. These galaxies follow predictable relationships between their colors and luminosities, creating a well-defined sequence in color magnitude space that reflects their shared evolutionary status. The red sequence is populated primarily by elliptical and lenticular galaxies that have exhausted their gas supplies and now shine with the accumulated light of stars formed early in cosmic history. Understanding the red sequence provides insights into how galaxies transition from active star formation to quiescent states, revealing the physical processes that govern cosmic stellar evolution. Galaxy morphology density relation demonstrates how galactic environments influence the types of stellar systems that develop in different cosmic neighborhoods, with elliptical galaxies preferentially found in dense cluster cores, while spiral systems dominate lower density regions. This relationship reflects the environmental processes that shape galactic evolution, including ram pressure stripping, tidal interactions, and merger rates that vary systematically with local galaxy density. The morphology density relation has persisted throughout cosmic history, suggesting that environmental influences on galaxy formation represent fundamental aspects of cosmic structure development. Understanding this relationship helps astronomers predict how galactic populations should vary between different types of cosmic environments and evolutionary epochs. Lyman break galaxies are distant star-forming systems observed at epochs when the universe was much younger, displaying the intense stellar formation activity that characterized cosmic evolution during earlier phases of cosmic history. These galaxies are identified through their distinctive spectral signatures, which result from the absorption of ultraviolet light by intervening hydrogen clouds along the line of sight. Lyman break galaxies often show compact morphologies and high star formation rates, creating stellar systems that were building their mass rapidly during the universe's more active youth. Their observations provide direct insights into how galactic assembly proceeded during cosmic epochs, when structure formation was more vigorous than in the present-day universe. Tidal disruption events occur when stars venture too close to supermassive black holes, creating dramatic but temporary increases in galactic nuclear activity as stellar material is heated and consumed by gravitational forces. These events can briefly transform otherwise quiet galactic centers into luminous beacons that outshine their entire host systems, demonstrating the violent potential that lurks within even the most peaceful stellar communities. The disruption process creates characteristic light curves and spectral signatures that allow astronomers to identify and study these rare events when they occur. Tidal disruption events provide unique opportunities to probe the properties of otherwise dormant supermassive black holes and understand how they interact with their stellar environments. Galaxy stellar mass functions reveal how cosmic matter has been organized into stellar systems of different sizes, providing fundamental constraints on models of cosmic structure formation and evolution. These statistical distributions show that the universe contains vastly more low-mass than high-mass galaxies, following power law relationships that reflect the underlying physics of gravitational collapse and stellar formation processes. The stellar mass function has evolved over cosmic time, with the most massive galaxies forming earlier and smaller systems continuing to assemble throughout cosmic history. Understanding these mass distributions helps astronomers predict how galactic populations should appear in different cosmic environments and evolutionary epochs. Galactic chemical evolution tracks how stellar nucleosynthesis has gradually enriched the universe with heavy elements, transforming the cosmic medium from its primordial composition of hydrogen and helium into the chemically complex environment that exists today. This enrichment process operates through stellar winds, supernova explosions, and other mechanisms that redistribute the products of nuclear fusion throughout galactic environments. Different types of stars contribute different elements to the enrichment process, creating complex chemical evolution patterns that vary between galactic components and stellar populations. Chemical evolution studies provide insights into the star formation histories of galaxies and help astronomers understand how cosmic environments have changed over time. Galactic conformity describes the tendency for galaxies to have similar star formation properties as their neighbors, suggesting that large-scale environmental influences extend beyond individual stellar systems to affect entire cosmic neighborhoods. This phenomenon indicates that galaxy evolution is influenced not only by local interactions, but also by more extended environmental factors that operate on scales of several megaparsecs. The conformity effect is particularly strong for central galaxies and their satellite systems, suggesting that shared formation histories or ongoing environmental influences create coordinated evolution among gravitationally associated stellar systems. Understanding galactic conformity helps astronomers develop more complete models of how cosmic environment influences stellar system evolution. Brightest cluster galaxy formation represents the ultimate expression of galactic cannibalism, where the largest cluster members grow through continuous accretion of smaller systems over cosmic time. These massive elliptical galaxies often display complex internal structure, including multiple stellar nuclei and extended stellar envelopes that record their merger histories. The formation process involves both direct galactic cannibalism and the accretion of intra-cluster stars that have been stripped from other cluster members during gravitational encounters. Brightest cluster galaxies serve as fossil records of cluster assembly, preserving evidence of the merger processes that built the largest gravitationally bound structures in the universe. Active galactic nucleus feedback regulates star formation in massive galaxies by heating or expelling the gas supplies needed for ongoing stellar birth, creating self-regulating systems where black hole activity controls galactic evolution. This feedback process helps explain why the most massive galaxies have ceased active star formation, despite their large gravitational potentials and abundant dark matter halos. The feedback operates through jets, winds, and radiation from accreting supermassive black holes, creating outflows that can remove gas from entire galactic systems. Understanding active galactic nucleus feedback is crucial for explaining how massive galaxies transition from active star formation to quiescent states and maintain their red colors over cosmic time. Galaxy downsizing describes the observational finding that more massive galaxies formed their stars earlier in cosmic history, contrary to naive expectations based on hierarchical structure formation models. This phenomenon suggests that the most massive stellar systems assembled rapidly during cosmic youth, while smaller galaxies have continued forming stars at later epochs. Downsizing may reflect the effects of feedback processes that shut down star formation more efficiently in massive systems, or environmental effects that influence how different types of galaxies evolve over cosmic time. The downsizing phenomenon has important implications for understanding how stellar mass assembly has proceeded throughout cosmic history. Galaxy quenching mechanisms describe the various physical processes that can shut down star formation in stellar systems, transforming actively evolving galaxies into quiescent red sequence members. These mechanisms include ram pressure stripping in cluster environments, morphological quenching through merger-induced gas consumption, and active galactic nucleus feedback that heats or removes star-forming gas supplies. Different quenching processes operate with varying efficiency in different cosmic environments, creating the observed diversity in galactic populations and their relationships to local density. Understanding quenching mechanisms is fundamental to explaining how galaxies evolve from active star formation to passive states, and how environmental factors influence this transition. Galactic archaeology studies use the chemical abundance patterns preserved in stellar atmospheres to reconstruct the formation and evolution histories of stellar systems. Reading cosmic stories written in the spectra of individual stars. This approach allows astronomers to trace how galaxies assembled their mass when they experienced major star formation episodes, and how they exchanged material with neighboring systems through mergers and interactions. Ancient stellar populations preserve chemical signatures from different epochs of galactic evolution, creating detailed records that can be decoded through careful spectroscopic analysis. Galactic archaeology provides unique insights into cosmic evolution that complement traditional approaches based on galaxy morphologies and integrated properties. Galaxy transformation processes operate continuously throughout cosmic history, gradually converting star-forming spiral systems into quiescent elliptical galaxies through various physical mechanisms, including mergers, environmental effects, and internal evolutionary processes. These transformations can proceed through multiple pathways, with different mechanisms dominating in different cosmic environments and evolutionary epochs. The transformation processes often involve dramatic changes in galactic properties, including morphology, stellar populations, and star formation activity. Yet they typically unfold over timescales much longer than human civilization. Understanding galaxy transformation helps astronomers explain the observed diversity in stellar system properties and predict how galactic populations will continue to evolve over cosmic time. Galaxy stellar halos extend far beyond the visible boundaries of their host systems, creating enormous spherical cocoons of ancient stars that trace the gravitational influence of dark matter across millions of light-years. These extended stellar populations are incredibly sparse, with individual stars separated by distances so vast that travelers between them would experience profound cosmic solitude. The halo stars follow highly elliptical orbits that carry them far above and below the galactic plane, creating three-dimensional stellar communities that exist in the quiet spaces between spiral arms. Many halo stars are among the oldest in the galaxy, preserving chemical signatures from epochs when the universe was young and metal-poor, making them living fossils of cosmic history. Dwarf galaxy pairs represent intimate cosmic relationships, where two modest stellar systems orbit one another in gravitational embrace, creating binary galaxies that evolved together over billions of years. These paired systems often show synchronized star formation activity, as their mutual gravitational influences trigger coordinated episodes of stellar birth that illuminate both companions simultaneously. The orbital dance between dwarf pairs unfolds with remarkable stability, allowing these cosmic couples to maintain their relationship across cosmic ages while individually evolving through internal processes. Some dwarf pairs eventually merge to form single, more massive systems, while others continue their orbital ballet indefinitely, creating long-lasting partnerships in the cosmic community. Galaxy surface brightness profiles describe how stellar light is distributed within galactic systems, revealing the underlying mass distributions and formation histories that shaped these cosmic architectures. These profiles typically show exponential decreases with distance from galactic centers, reflecting the physics of how stars and gas settle into stable configurations under gravitational influence. Different galaxy types display characteristic surface brightness patterns that encode information about their evolutionary histories, stellar populations, and structural components. Understanding these light distributions helps astronomers decode the processes that assembled galactic mass and organized stellar populations into the configurations we observe today. Peculiar velocity flows describe the motion of galaxies relative to the smooth expansion of the universe, revealing how large-scale gravitational structures influence cosmic motion on scales of hundreds of millions of light-years. These deviations from pure Hubble flow result from the gravitational attraction of massive cosmic structures, creating coherent streaming motions that carry entire galactic neighborhoods toward regions of enhanced matter density. The velocity flows provide direct evidence for the invisible architecture of dark matter that shapes cosmic structure, allowing astronomers to map gravitational influences that extend far beyond the visible matter distributions. Understanding peculiar velocities helps reveal how cosmic structure continues to evolve through gravitational processes operating on the largest observable scales. Galactic fountains describe the circulation of gas between stellar disks and extended galactic halos, creating cosmic respiratory systems that regulate star formation through cycles of ejection and accretion. Hot gas heated by stellar winds and supernova explosions rises from galactic planes into surrounding halos, where it cools and eventually falls back to fuel future generations of star formation. These fountain flows operate continuously over cosmic time, creating dynamic equilibria where galaxies maintain their star formation activity through self-regulating gas cycles. The fountain process also helps distribute heavy elements throughout galactic systems, mixing the products of stellar nucleosynthesis into the reservoirs that will form future stellar generations. Galaxy spin alignment describes the tendency for neighboring stellar systems to orient their angular momentum vectors in similar directions, suggesting that cosmic structure formation processes imprint preferred orientations on galactic populations. This alignment effect operates on scales much larger than individual galaxies, indicating that the formation of stellar systems is influenced by the large-scale tidal fields present during cosmic structure assembly. The alignment patterns provide insights into how cosmic web filaments and sheets channel matter and angular momentum during galaxy formation, creating correlations between galactic properties and their locations within the cosmic web. Understanding spin alignments helps astronomers reconstruct the environmental conditions that prevailed during galactic birth. Intragroup medium fills the spaces between galaxies in small groups with hot, tenuous gas that provides a shared atmospheric environment for member stellar systems. This medium is typically cooler and less dense than the intracluster gas found in large galaxy clusters, creating more gentle environmental conditions that allow group members to retain their gas supplies for extended periods. The intragroup gas often shows evidence of enrichment by stellar winds and supernova from group galaxies, creating a chemically complex medium that records the collective stellar evolution history of the entire group. This shared gaseous environment facilitates ongoing interactions between group members while providing reservoirs of material that can fuel future star formation episodes. Galaxy stellar velocity dispersions measure the random motions of stars within galactic systems, providing fundamental insights into the gravitational potentials and mass distributions that govern stellar dynamics. These measurements reveal how stellar populations respond to the combined gravitational influences of visible matter and dark matter, creating velocity patterns that encode information about galactic structure and formation history. Higher velocity dispersions typically indicate more massive systems or regions where gravitational forces are particularly strong, while lower dispersions suggest more relaxed gravitational environments. Understanding stellar kinematics helps astronomers probe the dark matter content of galaxies and test theories of how these invisible halos influence visible stellar populations. Satellite galaxy planes describe the flattened distributions often observed around massive central galaxies, creating disk-like arrangements of smaller stellar systems that challenge expectations based on simple dark matter halo models. These coherent structures suggest that satellite accretion may follow preferred directions related to the cosmic web or large-scale tidal fields, rather than occurring isotropically as predicted by standard cosmological simulations. The satellite planes often show evidence of coordinated orbital motion, with multiple satellites sharing similar orbital orientations that persist over cosmic time. Understanding these structures provides important tests of galaxy formation models and insights into how cosmic environment influences the assembly of galactic systems. Galaxy metallicity gradients describe how the abundance of heavy elements varies with distance from galactic centers, creating chemical patterns that record the history of stellar evolution and gas-mixing processes within stellar systems. These gradients typically show higher metallicities in central regions where star formation has been most intense, with decreasing abundances toward galactic outskirts where stellar evolution has proceeded more gradually. The gradient patterns encode information about how efficiently galaxies mix their interstellar media and how star formation activity has varied across different galactic regions over cosmic time. Understanding chemical gradients helps astronomers reconstruct the internal evolution histories of galaxies and test models of how stellar feedback processes redistribute heavy elements. Brightest galaxy cluster member evolution describes how the most luminous systems in rich clusters continue to grow through ongoing accretion of smaller galaxies and intracluster stellar material. These massive central galaxies often display evidence of recent merger activity, including disturbed morphologies, multiple stellar nuclei, and extensive stellar envelopes that extend far beyond typical galactic boundaries. The growth process operates continuously over cosmic time, with central galaxies slowly accumulating the stellar debris from disrupted cluster members and the gradual infall of intact satellite systems. This ongoing evolution makes brightest cluster galaxies among the most dynamically active stellar systems in the universe, despite their appearance as ancient, evolved galactic populations. Galaxy group velocity dispersions measure the random motions of member galaxies within gravitationally bound groups, providing insights into the total masses and dynamical states of these intermediate-scale cosmic structures. These measurements reveal how group members respond to their shared gravitational environment, creating velocity patterns that reflect both the group's mass distribution and its evolutionary history. Higher velocity dispersions indicate more massive groups or systems that have undergone significant dynamical evolution, while lower dispersions suggest younger or less massive associations. Understanding group dynamics helps astronomers probe the dark matter content of these systems and trace how they evolve from loose associations into more tightly bound configurations. Cosmic void galaxy properties differ systematically from those of stellar systems in denser environments, reflecting how the sparse gravitational fields and reduced interaction rates in underdense regions influence galactic evolution. Void galaxies often maintain higher gas fractions and more active star formation rates than their counterparts in clusters and groups, having avoided the environmental processes that strip gas and quench stellar birth in denser regions. These systems frequently display bluer colors and more irregular morphologies, suggesting that isolation preserves certain aspects of galactic youth and allows continued evolution through internal processes. Studying void galaxies provides insights into how environmental density affects stellar system properties and reveals what galaxies might look like in the absence of significant external influences. Galaxy luminosity functions describe the relative numbers of stellar systems with different brightnesses, providing statistical frameworks for understanding how cosmic light is distributed among galactic populations. These functions typically show that faint galaxies vastly outnumber bright ones, following power law relationships that encode fundamental information about galaxy formation processes and cosmic structure development. The luminosity function has evolved over cosmic time, with changes reflecting how stellar populations have aged and how galaxy mergers have redistributed light among different mass scales. Understanding these statistical distributions helps astronomers predict galactic populations in different cosmic environments and evolutionary epochs. Interacting galaxy morphologies display the gravitational sculptures created when stellar systems encounter one another, producing some of the most visually striking structures in the cosmic landscape. These distorted configurations often feature long tidal tails, bridges of stellar material connecting the participants, and rings or shells that mark the gravitational waves propagating through the stellar distributions. The morphological evolution during interactions follows predictable patterns that depend on the masses, orientations, and orbital parameters of the participating galaxies, creating a rich taxonomy of merger-induced structures. These gravitational artworks provide laboratories for studying how stellar systems respond to external forces and how galactic mergers redistribute matter and energy. Galaxy stellar mass-to-light ratios reveal how efficiently different types of stellar systems convert their mass into observable light, providing insights into stellar populations, dark matter content, and evolutionary histories. These ratios vary systematically with galaxy type, with elliptical systems typically showing higher mass-to-light ratios due to their older stellar populations and higher dark matter fractions. The ratios also depend on the wavelength of observation, as different stellar populations contribute differently to galactic light at various colors. Understanding mass-to-light relationships helps astronomers estimate total galactic masses from brightness measurements and probe how stellar evolution affects the visible properties of cosmic stellar communities. Central galaxy quenching describes the process by which massive galaxies at the centers of dark matter halos cease their star formation activity, transitioning from blue, actively evolving systems to red, quiescent stellar populations. This quenching often occurs more efficiently in central galaxies than in satellite systems, suggesting that internal processes rather than environmental effects drive the transition in these massive stellar systems. The quenching mechanism may involve feedback from central supermassive black holes, exhaustion of cold gas supplies, or virial shock heating that prevents further gas accretion. Understanding central galaxy quenching helps explain how the most massive stellar systems evolve and why they dominate the red sequence of cosmic stellar populations. Galaxy cluster mass functions describe the abundance of gravitationally bound systems with different total masses, providing fundamental tests of cosmological models and insights into how cosmic structure has evolved over time. These statistical distributions show that less massive clusters are much more common than their massive counterparts, following relationships that depend on the underlying cosmological parameters and dark matter properties. The mass function has evolved significantly over cosmic history, with the most massive clusters forming relatively recently as smaller structures merge together. Understanding cluster abundances helps astronomers constrain models of cosmic evolution and probe the nature of dark matter and dark energy through their effects on structure formation. Tidal galaxy disruption occurs when stellar systems venture too close to massive neighbors, experiencing gravitational forces that overcome their internal cohesion and strip away stellar material. This process typically begins at the outer edges of the victim galaxy, where stars are less tightly bound and more susceptible to external tidal forces. The disruption proceeds gradually, with successive close approaches removing additional stellar material until only a dense central core remains, or the system is completely destroyed. The stripped stars often form spectacular tidal streams that can extend across millions of light years, creating some of the most extended structures associated with individual galactic systems. Galaxy formation efficiency describes how effectively cosmic environments convert their available matter into stellar systems, revealing important constraints on the physical processes that govern cosmic structure development. This efficiency varies dramatically with environment, halo mass, and cosmic epoch, reflecting the complex interplay between gas cooling, star formation, and feedback processes that regulate galaxy assembly. The efficiency is typically highest in intermediate mass halos, where gas can cool efficiently, but feedback processes are not yet strong enough to prevent ongoing star formation. Understanding formation efficiency helps astronomers predict where galaxies should form and why certain cosmic environments are more productive at creating stellar systems than others. Supergiant shell structures in some galaxies create enormous cavities in the interstellar medium that can span thousands of light years, representing some of the largest coherent features within individual stellar systems. These shells typically form through the collective effects of multiple supernova explosions and stellar winds from massive star clusters, creating expanding bubbles of hot gas that sweep up surrounding material into dense, shell-like configurations. The shells can persist for tens of millions of years, slowly expanding and cooling as they propagate through the galactic medium. These structures demonstrate how stellar feedback can organize interstellar matter on galactic scales, creating architectural features that influence subsequent star formation and gas dynamics. Low metallicity galaxies preserve chemical conditions reminiscent of earlier cosmic epochs, maintaining stellar populations with elemental abundances similar to those that existed when the universe was much younger. These systems often display active star formation despite their primitive chemical compositions, suggesting that they have avoided the enrichment processes that have modified most other galactic environments over cosmic time. Their low metallicities may result from inefficient star formation that produces fewer heavy elements, or efficient gas loss mechanisms that remove enriched material before it can be incorporated into new stellar generations. Studying these chemically primitive systems provides insights into how galaxies evolved during cosmic youth and how environmental factors influence chemical evolution. Galaxy halo occupation statistics describe how stellar systems populate dark matter, halos of different masses, providing fundamental connections between visible galactic properties and underlying cosmic structure. These relationships show that more massive halos typically host more luminous central galaxies and larger numbers of satellite systems, but with significant scatter that reflects the stochastic nature of galaxy formation processes. The occupation patterns have evolved over cosmic time, as galaxies have grown and merged within their dark matter hosts, creating complex relationships between halo properties and observable galactic characteristics. Understanding halo occupation helps astronomers predict how galaxies should cluster and provides tests of galaxy formation models. And now, as our gentle journey through these galactic wonders draws to a close, let your thoughts drift like starlight through the cosmic dark. We've wandered together through spiral arms that turn with the patience of deep time, past ancient stellar cities that have been burning since the universe was young, and into the quiet spaces where dwarf galaxies orbit their companions like faithful cosmic moons. Each galaxy we've encountered carries its own story, its own rhythm, its own place in the vast tapestry of space and time. As you rest tonight, remember that somewhere out there, billions of these magnificent stellar islands continue their slow dance through the cosmos, their light traveling across impossible distances just to reach us here on this small blue world. Sweet dreams, and thank you for exploring the universe with me.